This video will cover limiting reactant, theoretical yield, and percent yield. Please read the OER textbook chapter section 7.3 for more detail. The homework that associated with this lecture video is homework 7.3. In the previous chapter 7.1, we learned how to write chemical equations and also balance chemical equation. And the chapter 7.2, we use the coefficient from the balanced chemical equation to help us do calculation by using the stoichiometric ratio that allow us to convert between reactant or reactant product, or between product, right? And in this chapter section, we are going to do similar calculation to 7.2. The difference between 7.2 and 7.3 is that 7.2, the given information will be just one. Okay, so there will be one given information. And that information can be either reactant that is given or the product that will be given, and asking for something, right? So it can be asked in like how many mole that is can made, right? Or how many grams, right? Or it can ask for the number of molecules. Okay, so this type of calculation is already covered in the previous video. Okay, so the difference for chapter 7.3 is that the calculation is similar, but 7.3, you are going to be given two information. And this information would be the information of the reactant. Okay, so at least, okay, so I have to say at least two information, because depending on how many reactant do we have, right? So how many reactant amount that is going to be provided. So in this case, when the amount of the reactant are given more than one, okay, so let's say like if you have like two molecules react and the information are given for both molecule, we would need to determine first which one is going to be limited and which one is going to be in excess, because if you have something in excess, it's going to have some leftover, right? And if we have the limit amount of something, that means that molecule would be all consumed after the reaction, right? So that means in this case, we need to determine which one is going to be limited, and that's what we call limiting reactant. And the limiting reactant would determine the amount of product that can be made, which is going to be called theoretical yield. And we're going to take a look at the percent yield also. To understand the concept of limiting reactant, theoretical yield, and percent yield easily, I'm going to use how to make bike as analogy. Okay, so let's say if we want to make one bike, let's say that it's called for 2 wheels and a frame. Okay, so the question is, if you have the starting material, you start with 10 wheels and 20 frame, how many bikes can we make then, right? So that would be the question here. So similar to the chemical problem that you are going to encounter in just a few minutes. Okay, so pretty much the two amount of the reactant or the starting material will be given to you, and you will need to determine how much product can be made exactly from what is given, right? So that's what we're going to take a look at. Okay, so what we are going to do is we are going to use the given information of the two reactant to help us determine the amount of product that can be made. Okay, so in this case, if you're looking at the number of wheels, 10 wheels, and it's required 2 wheels per one bike, right? So that means in this case, per 10 wheels that we have, we can make only 5 bicycles. And if you're looking at number of frames, right, we have 20 frames, is 1 frame per one bike. So that means if you have 20 frames, you should be able to make 20 bike, right? But in this case, you will see that the answer would be one of these. It's not going to be both combined. The reason for that is because the number of wheels is unlimited. Okay, because it requires 2 wheels per one bike. So that means if you have 10 of them, you are going to be able to make only 5, right? Because in this case, the number of frame would be in excess. So that means at the end of the process, the number of wheels will all be consumed, and you are going to have leftover amount of the frame left. So that means in this case, the limiting reactant is the one that is going to be consumed at the end of the reaction, and the reactant that are in excess would be whatever leftover that will not react, right? And the maximum amount of product that we are going to, that can be made is this is what we call theoretical yield, or the amount that theoretically can made, right, from the limiting reactant. In other words, the limiting reactant is the reactant that limit amount of the product that can be made. Okay, so again, the reason why I call maximum product, because this is the maximum possible amount of the product that can be made, is only going to be 5 of them. It's not going to be 20 because we don't have enough number of wheels to make 20 bike. Okay. In reality though, this process might not yield 5 bicycle. The reason for that is might be because one of the wheels got like defected or something, or like the tire is flat or whatever. So let's say that we can actually make only 4. So these 4 bikes is going to be referred as the actual yield. Okay, so in the experiment, the actual yield would be the amount that obtained from the experiment. Okay, so experimentally, this is how much you can make. Okay, theoretically would be the amount that you are going to obtain from the calculated value that is going to determine from the limiting reactant. Okay, so this is the theoretical value, this is the experimental value. Okay, so the percent yield is what we use to determine the efficiency of the reaction. So in this case, you can use the actual yield divided by theoretical yield multiplied by 100 to give you the percent yield. So that means in this case, you are going to make about 80% efficiency of making bike in this case. Note that in reality, the percent yield will not equal to 100%. Sometimes percent yield can be higher than 100%, and sometimes the percent yield can be lower than 100%. But most often time, from the experiment, you are going to obtain percent yield less than 100%. The reason for that is because the reaction, when the reactants are react together, they might not go all the way to the completion, or sometimes when the reactant react together, it might provide some side reaction that produce some other type of the product that can decrease the mass of the desired product you are looking at, making the percent yield to be lower than 100% yield. Okay, so in the case where the percent yield is higher than 100%, that is when you are going to encounter with something that can absorb water, because if the amount of product absorbing water, the mass of water is added to the mass of the product, making the percent yield to be higher than 100%. Now let's take a look at the cooking recipe to help us understand the limiting reactant concept a little bit better. So in the previous example of how to make bike, you will see that it's required only 2 reactants. In this case, you will see that it's involved with several ingredients or several reactants in order to make one potato salad. Okay, so it doesn't matter how many reactant is given or is provided or is involved in chemical reaction, the concept of this will still be the same. Okay, so what do we mean by that? Okay, so in this case, in order to figure out what should be the amount of potato salad that can be made, you are going to use all of these ingredients that you have and use the recipe to help you determine, right, of how many potato salad you have. Let's say that you obtain this from the grocery store, right? This is the amount of each ingredient that you have. What you will need to do is that you will need to use each of those reactant. Okay, so remember, reactant are on the left-hand side, product is on the right-hand side. You will need to use each of those reactant, okay, to do calculation to see how much product it can be made. Okay, so in this case would be how much potato salad can be made. So similar to when you're looking at the number of wheels and to the number of bicycle that can be made versus the number of frame to the number of bicycle that can be made, we are going to do the same thing, but in this case we're going to look at all of these 5 ingredients at the same time. Okay, so we're going to compare all of this to the number of potato salad. Okay, so in order to do this is how you would set up for the chemical reaction as well. These coefficient in front of each of these would be similar to the balanced chemical equation that we learned, right? When you are doing the balancing chemical equation, it's come from the same thing. So these are the recipe, right? So pretty much it's the recipe. So if you have 18 potatoes, okay, in order to calculate to see how much potato salad can be made, normally you can just do it in your head and get the number of potato salad, right? Because these are the whole number, is easy to deal with. But when you are doing calculation for the chemical reaction that you are going to see in the next example, you will see that the number will not be in a whole number, which means that it's going to be a little bit harder to do it in your head. Okay, so you need to actually write it out and do the unit cancellation, so that way you will not make any mistake. And also on the exam, I require you to show work as well. So that means you will need to show me unit cancellation to get the full credit for that. Okay, so how do we set that up? Okay, so in this case, we are going to do the same thing similar to the previous chapter section, where you are going to set up the calculation by using the mole to mole ratio, right? So in this case, you are going to use the recipe ratio between potato and potato salad. Okay, so if you have 18 potatoes, the conversion factor between potato and potato salad would be 6:1, right? So if you have 16 potato, it's going to require 6 potato for 1 potato salad. So that means in this case, if you cancel the unit of potato, you're going to have potato salad left, which is going to come out to be 3 potato salad according to the recipe, right? So again, I am comparing one ingredient at a time. Okay, so I'm going to use one ingredient at a time, and we need to use each of those ingredients to see how much potato salad that we can make. Okay, so because I'm going to tie this back into the chemical equation in the next example. Okay, so you can do the same thing for pickle as well. You bought 5 pickles, and it's required 5 pickles for 1 potato salad. So that means in this case, if you set it up, you are going to end up with 1 potato salad, right? So according to the number of pickle that you have. Do the same thing for the onion as well. Okay, so you are having 2 onions, so it's required only 1. So therefore, in this case, per the recipe, if you have 2 onions, you should be able to make 2 potato salad, right? Continue doing with mayonnaise, okay, and also with mustard as well. Okay, so that means in this case, these are the number of potato salad that from calculation. But which one exactly should be our final answer, right? So which one exactly that that we could make, right? So which one exactly? So should we add all of them together, or should we pick the highest value, or should we pick the lowest value? The answer is you are going to need to pick the least amount of potato salad from your calculation. The reason for that is because this is the maximum possible amount that we can make, because we have limit amount of pickle, right? So that means in this case, pickle is the limiting reactant, because the amount of pickle limit amount of the product or amount of potato salad that can be made. 1 potato salad would be the theoretical yield. Okay, so this is the maximum possible amount that we can make. Again, the reason for that is because you cannot make 5 potato salad, because you're going to run out pickle first, right? You are going to be able to make only 1. Same thing, you're not going to be able to make 4 potato salad, because you're going to end up running out pickle, because the recipe requires 1 to 5, right? You are going to only make 1 potato salad in this case. Okay, so that's how we are going to look at in the next example. Doesn't matter what problem give you, right? It doesn't matter how many reactant. All you have to do is start with the reactant and calculate to see how much product is can made. Okay, and the least number from the calculation, that would be the possible amount that we can make. Never ever add them together, because you cannot make that much, right? Because you're gonna end up running out pickle first. Okay, pick only the least amount one. Okay, so another thing that I would like to point out is that when we look at limiting reactant, the answer have to be one of these reactant. Okay, theoretical yield would be the yield of the product. Okay, so those are the 2 different things that students get confused sometimes. Okay, so just make sure that you understand and be able to differentiate them. Okay, so I'm going to use similar process here for the chemical for the next example. So pretty much in this case, we have 5 ingredients. You set up 5 calculation, right? And then pick the one that yield the least number of product, which is going to be the maximum possible amount that we can make, right? And then the ingredient for that would be the limiting reactant. So I'm gonna do the same thing for our example next. Okay, so let's tie that back to the chemical equations now. So we have the combustion reaction between pentane and oxygen, okay, yield carbon dioxide and water. Okay, so first step will always be the same step that we did in the previous lecture video. make sure that this reaction is balanced, right? If it's unbalanced, you need to balance it first because the correct calculation come from the balance coefficient, okay? So in this case, if you're looking at this, you have 5 carbon, you have 1 carbon. Clearly, this equation is unbalanced. So that means you have to balance it first. Which element you should avoid? The answer is it should be oxygen, right? You should avoid oxygen because if you're looking at the product side, oxygen appear in both molecule of the product. It make it more complicated to try to balance those. Okay, so avoid oxygen first. So that means you can either go with carbon or hydrogen first, right? So I'm just going to go with carbon. So we have 5 carbon here. I'm going to add 5 in front of carbon dioxide. Okay, so now we have 5 carbon. We have 12 hydrogen, so I'm going to add 6 for this. Okay, so now we have 12 hydrogen. 5 times 2 for oxygen, that would be 10, right? So 5 times 2, that would be 10 oxygen. Okay, 6 water, that would be 6 oxygen. Okay, add these two together, you're gonna have 16 oxygen total. So that means in order to make this to be 16, you need 8 coefficient in front of the oxygen. Okay, so this equation now already balanced. Okay, so after you balance the chemical equation, the next thing would be look at what are the given information, right? So in this case, if you're looking at this, it's asking for carbon dioxide, so it's asking for the product. It's given 2 information, right, of the 2 reactant. Hey, because the information are given for both reactant, therefore you will need to find the limiting reactant. You will need to find which one is going to be all consumed, right, at the end of the reaction, because one of them is going to be all consumed, right, and that amount is going to convert into the product, right, and there will be one of them that is going to be in excess. That means at the end of the reaction, there will be some extra left. Okay, so that's what it means. Okay, again, in order to find limiting reactant, we're gonna do the same thing that we did previously with the potato salad, right? So you need to set up calculation for each ingredient. In this case, you are going to set up calculation for each reactant. Okay, so we're gonna start with, let's say like we're gonna start with C5H12 pentane. So what you're gonna do is, it's given in grams, so you are going to do the same calculation that we did in the previous lecture video. Okay, so we are going to convert these grams into mole by using molar mass, right? This number come from the periodic table where you add all these carbon and hydrogen together. The mass of this would be this much, right, in 1 mole of pentane. After you convert from grams to mole, the next thing is, because we are looking at the grams of carbon dioxide, right, because that's what it asked us, you are going to have to convert to mole of carbon dioxide. It doesn't ask for oxygen, therefore never combine it. Okay, so separate these calculation because you have 2 different reactant. You need to do 2 different calculation for each reactant. Never combine these 2 because these 2 are not the same. They do not require the same ratio, right? So you need to set up the 2 different calculation for this. And because again, it's asking for grams of carbon dioxide, so therefore I'm going to convert this all the way to grams of CO2 because that's what it asks, right? If the problem asking for number of mole, then you're just gonna stop right here. If the problem asking for the number of molecule of carbon dioxide, then you're going to use Avogadro's number to do the next step of the calculation. So watch out for the problem, right? What does it ask you exactly? You already learned this. Just make sure that you know how to answer the problem correctly, because if you don't read the question carefully, you are going to end up doing extra work that it doesn't require, and that is time consuming, and that's when you will not be able to finish the exam on time. Okay, so watch out for that. Okay, so in this case, we know that the recipe requires 1 mole of pentane, right? It's going to produce 5 mole of CO2. So that is going to be the ratio that go into here, right? So this is from periodic table. This is from the balanced chemical equation. The next thing is, if you cancel the unit, you will see that grams cancel out, right? Mole cancel out. You have mole of CO2 left. It doesn't ask for moles of CO2. It's asking for grams. Therefore, you will need to do the next step. Okay, so find out the grams of CO2 by looking at the periodic table, add the number of the mass of carbon and oxygen together, which is going to come out equal to 44 grams. Note that the common mistake would be many students would multiply this 44 by 5 because they see, oh, it's 5 CO2, so let me multiply this by 5. Do not do that, okay? Don't do that, because this is molar mass. The definition of molar mass is the mass of 1 mole. It's a mass of 1 mole of the substance. Okay, so you need to leave it as mass of 1 mole. Do not multiply by 5. This coefficient 5, we already use it, right? We already use it. It's a count in this step right here. Okay, so again, this coefficient is going to be part of the stoichiometric ratio. Do not incorporate this 5 with the molar mass. Never ever incorporate this 5 with the molar mass. Okay, so again, don't do that. Okay, so in this case, when you are showing me work on the exam, you need to show me each of these steps because there are points associated with this. Okay, so for example, if you forgot this one, it would be 1 point deduct, right? So this whole thing would count 1, 2, 3. So 3 points for that. 4 points for correct answer. 5 points would be correct suffix and unit, right? So that means this whole setup right here would worth 5 points already. Okay, so including correct answer and unit and suffix. Okay, so that means in this case, make sure that you give me all the steps. Okay, so all the conversion, I need to see the unit the unit cancellation to give you point, because when I assign point, there is always point breakdown for all of those. Without showing me work, again, you are going to get just 1 point out of the correct answer, right? Because each of these contain point as well. If you don't show me any of these, you already missed like 3 points out of 5, right? So just make sure that you actually show me work for that. Okay. So if you do calculation, so pretty much you are going to multiply the top number and then divide by the bottom number. Okay, so this is what you are going to get. Then you are going to do the same thing with oxygen, right? So you already use one ingredient, similar to, again, calculation for the potato salad, right? You go with one ingredient at a time. Okay, so same thing for that. Okay, so we're gonna do with the oxygen also. Start with the grams of oxygen. Next, you are going to find out molar mass of oxygen. So in this case, again, it's going to be mass of 1 mole, not mass of 8 mole. Okay, so don't incorporate 8 here. This number 8 is going to be incorporated in the next step when you are using the stoichiometric ratio, right? So this would be 8 to 6, right? So 8 mole of oxygen per, oh, sorry, not 6, 5. We are looking at carbon dioxide. So it would be 8 per 5 mole of carbon dioxide. Okay, so then we're not going to stop here because asking for grams. So we're going to go all the way to grams. Okay, so in this case, if you go all the way to grams, it's going to be 44 grams of CO2. Do this calculation, is going to come out equal to about 18 grams of CO2. The next question is, which one exactly would be the amount of grams of CO2 that could form? Do you choose the maximum amount, or do you choose the highest amount or lowest amount, or should we combine them together? The answer is only 17.9 grams of CO2 can be made. The reason for that is because you have limit amount of oxygen. Okay, so oxygen is the limiting reactant that limit amount of product, right? This is how much oxygen you have. You can make only this much of CO2. You don't have enough oxygen to make that much of CO2. Therefore, oxygen, which is the reactant, is the limiting reactant. Okay, and this amount of CO2 that calculated from the amount of oxygen would be called the theoretical yield. This is the theoretically, this is how much you can make, right, or you can obtain. Okay, so that means at the end of the reaction, oxygen molecule would be all consumed. There would be no oxygen left at the end of the reaction. Okay, and at the end of reaction, you are going to observe some of the pentane molecule left, because this is what in excess, right? You have way more than you have this in excess more than the oxygen available. Okay, so that's what it means here. On Newton homework, it might not ask you to calculate all the way to grams of CO2. Note that if Newton homework asking you to calculate mole or atoms, you just need to read the problem carefully to actually calculate for those. Okay. For example 3 on page 134, I would like you to pause the video and complete these example yourself. Okay, before you check the answer, against my answer, I would like you to actually start working on this as the evaluation of your understanding. Again, don't watch this video unless you actually complete this, because when you are taking the exam, you will not be able to start, right, if you don't understand it. So same thing here, if you get stuck, like if you like struggling with this, it's already indicated you don't actually understand it at all, right? So that means try to do it yourself first. Okay, so try to complete as much as possible before you actually look at the answer. Okay, so let's do it now. Let's pause the video and resume it again when you finish. All right, let's take a look at your answer. Okay, so check your work with me. Okay, so in this case, we are looking at the synthesis of ammonia. Okay, so this is the ammonia right here. It's require hydrogen gas react with nitrogen gas, right? And look like if you check the chemical equation, it's already balanced, right? So we have 6 hydrogen, we have 2 nitrogen, so it's already balanced. Okay, so I don't need to worry about that. The thing that we are going to take a look at next is the problem, right? So the problem asking us mass in grams of the ammonia, which is this one right here. And it's giving us information of the amount of hydrogen gas and also the amount of nitrogen gas as well. Okay, so in this case, what you are going to do is you are going to find out the limiting reactant, right? So similar to what we did earlier, I'm going to start with the amount of hydrogen gas first. It's giving us in kilograms, so don't forget to convert that into grams. Okay, so every kilogram is equal to 1,000 grams. Then you are going to convert grams to mole by using the molar mass of hydrogen. Okay, and after you know mole of hydrogen, then you are going to convert mole of hydrogen to mole of ammonia, because that's what it's asking for, right? Asking for mole of ammonia. So this one is 3:2. Okay, and after you get the mole of ammonia, then we are going to look at the molar mass of the ammonia, because every mole of ammonia would contain this many grams, right? Come from the mass of nitrogen and hydrogen add together. Okay, if you do this calculation, multiply everything on top, divide everything on the bottom, you are going to get these many grams of ammonia. Okay, so again, on the problem, on the exam, it might asking you in grams, or it might ask you to stop just mole, or it might asking you the number of molecule. You just need to know what you need to go next exactly. Okay, so the conversion would be the same process that we learned earlier. Okay, so again, the understanding of this is required the previous knowledge of the conversion between grams to mole, mole to grams, mole to molecule, molecule to mole, right? So you already learned this. Okay, so it's just refer back to the previous chapter section. Okay, once you finish calculation from hydrogen, right? Once you obtain the product, amount of product from hydrogen reactant, then you are going to continue with the next reactant. The next reactant is nitrogen. Again, set up 2 separate equations. One is for the first reactant, second one is for the second reactant. You cannot combine these two. Okay, so you need to set up them separately. Okay, so I emphasize this already, so do not make this mistake on the exam. Again, another thing is do not incorporate 3 to the molar mass, because molar mass is the mass of 1 mole. These 3 right here of this coefficient will be included in the stoichiometric ratio already. So that's what you are going to need to show me. Okay, so do the same thing, because provided in kilograms, you are going to convert kilograms to grams, right? Using molar mass to convert to mole, using mole ratio to convert to mole of ammonia, using ammonia molar mass to get the grams of molar mass, or to get the grams of the ammonia, right? If you're looking at this, we see that if you have 5.5 kilograms of hydrogen, you can make 2.94 times 10 to the 4th grams of ammonia. If you have 31.5 kilograms of nitrogen gas, it can make 3.83 times 10 to the 4th grams of ammonia. So what should be the mass of ammonia that could be formed exactly then? The answer would be this amount, right? So it can be formed only 2.94 times 10 to the 4th grams. The reason for that is because you have limit amount of hydrogen. Okay, so the hydrogen in this case would be the limiting reactant. Again, the reason for that is because we have limit amount of hydrogen gas. Therefore, only this much of ammonia can be made. You don't have enough hydrogen to make that much. Therefore, in this case, this is the theoretical yield. Okay, so let's practice this one more with the next example. Okay, so I'm going to give you some few minutes here. Okay, so pause the video again and complete this on your own. Okay, so I encourage you to do this. Okay, so again, you will need to do it. Okay, so I'm not there to watch you doing this, but please complete this, okay, before you resume the video. All right, let's check the answer with me. Okay, so it's giving us the reaction between titanium and fluorine gas that produce titanium 4 fluoride. Okay, so the problem giving us grams of titanium, which is the reactant, and also grams of fluorine as well. So same thing. This is involved with the limiting reactant. How do I know? Well, because the reactant, two of the reactant information are given, not just one, but it's given both of them. So therefore, in this case, we are going to set up calculation for both of them. But before we do that, make sure that the chemical equation already balanced. So 1 titanium, that's good. 4 fluorine, that's good. So that means we can just use this now without have to balance it. Okay, so set up the same thing that we did earlier. Okay, so grams of titanium that is given using the molar mass of titanium, and don't forget to include the mole to mole ratio. Okay, so even though it's 1 to 1, you still need to show me, because each of these steps would worth points. Okay, so I'm going to walk you through how many points total that I'm going to give, right, if this were for the exam. Okay, so and after you get more of what it's asking for, right, because it's asking for what grams of titanium 4 fluoride, so it's asking for this, right? So that means in this case you are going to convert from grams to mole to mole of another species, right, using the stoichiometric ratio, and then use the molar mass of titanium 4 fluoride to actually get the grams of titanium 4 fluoride. Okay, all right, so same thing. When you finish with one reactant, it's giving you another reactant too. So that means you will need to also calculate for the second reactant as well. Okay, so grams to mole, right? Mole to mole using the mole ratio, and then using the molar mass. Okay, together, these two, right? You are going to see two different amount of titanium fluoride. Which one that is could form exactly? The answer would be only 8.15 grams, right? Because you have limit amount of fluorine. So the fluorine is the limiting reactant that limit amount of the product that can made. You don't have enough fluorine to make that much of titanium fluoride. Therefore, in this case, the answer would be just 8.15. Never ever add these two together. Okay, so you need to choose the least amount, because the least amount is the maximum possible amount that can be made, because you have the limit amount of fluorine. At the end of reaction, fluorine will be all consumed. You don't have any of this left because already convert to the product. The only thing that we are going to have left would be the amount of titanium. Okay, so this titanium would be in excess. Okay, if I assign point for this problem, it would be 1 point for this conversion, right? So 1, 2, 3, 4 for the correct answer. 5 would be unit sig fig, right? So this whole thing would be 5 point already. This whole thing would be 5 point already, right? So together would be 10 point. 10, 11, 12, 2 point would come from choose the correct theoretical yield. Another 2 point would come from providing me the correct limiting reactant. Okay, so that means in this case, like it's probably be like about like 10 to 15 point problem, right? So on the exam, so make sure that you understand how to do this. Okay. All right, so number 5, I'm going to walk you through number 5. So similar to the previous example that we did earlier, but in this case, we are going to calculate for percent yield. Remember the formula of the percent yield that I mentioned earlier when we talk about making bicycle, right? So we are going to use the same concept here. Okay, so, but we are going to tie this into chemical reaction. So we have iron oxide that react with carbon monoxide, right, to give us iron and carbon dioxide. So the problem giving us information of both reactant, right? So one is the iron oxide, the other one is giving us is the grams of carbon monoxide. So in this case, we know that this is going to involve with the limiting reactant, because both reactant information are given. Therefore, we need to determine which one is going to be all consumed, right? Which one is going to be limited. Okay, so in this case, it talk about produces this much of the product. Hey, this is product though. These two, yeah, these two are reactant, right? So these two are reactant. This one is the product. So why would they give us the amount of product? Okay, so that is the amount of product is given or provided on the in the problem would be the actual product that is going to that we will need to use. Okay, so pretty much asking for percent yield, and we already know percent yield would be actual yield divided by theoretical yield multiplied by 100%. So that means the amount that is provided for the product, right? Because we are looking at the product in this case. Okay, so this is the amount of the product actually made, right? This is amount of product that theoretically can be made, right? So we are looking at the product. Okay, so what are the product is Fe, right? And CO2. But the only information it's giving us is only the Fe. So that means it's asking for the amount of the product, which is of the iron for both. Okay, because when you divide something, you have to use the same thing, right? So in this case, we are going to look at iron actual yield and iron theoretical yield. Okay, so note that again, these two are given. These two are the reactants that we are going to need to use, and the amount of iron, which is the product, would be the actual yield. Okay, so pretty much what you are going to do is, first step would always be the same, right? So check whether the chemical equation balanced or not. Second one is because the two reactants are given, you will need to find limiting reactant, because finding limiting reactant will allow us to obtain the theoretical yield, which is this, right? Theoretical yield comes from the calculated value, remember? So that means in this case, we need to find out that. But what is the actual yield then? That is provided from the problem, right? The problem said that we actually produce this much, right? So that means this is going to be the actual yield. Okay, so that means we already know actual yield. The only thing we don't know is theoretical yield. So go ahead, find out theoretical yield the way that we did earlier, right? So pretty much you are going to set up two equations, one coming from the first reactant, okay? Convert the first gram of the reactant to its mole, and then use mole to convert to mole of the iron, because that's what the problem asking us, right? Then multiply by the molar mass of iron. Eventually, you are going to get 117 grams of iron. Do the same thing with the second reactant, right? Because you have to calculate for all ingredients, right? So do the same thing for the second reactant that comes from carbon monoxide. Okay, so set up the same equation, except you need to change the ratio, right? So the ratio between these two. And you are going to get this much of the iron that can be made. Okay, so again, what number should be the theoretical value? Should we add them together? Or should we choose the big number, or should we choose the lowest number? The answer again would be the lowest number, right? The lowest number from the calculation would be your theoretical yield, because you have limit amount of carbon monoxide to make that much, right? You can make only this much. Therefore, in this case, all you need to do is plug in 114 grams as the theoretical yield and plug in 72.3 grams as the actual yield. Multiply them by 100, you are going to get 63.4% for this problem. Okay, so again, for calculation for percent yield, right? So if the two reactants are given, then you are going to need to find the theoretical yield first, okay, in order to put it into this equation right here. So the problem that you are going to encounter on the exam, it would be either two information of the two reactants are given, or just one. Okay, so if you are given just one information, then you don't need to find out the limiting reactant, right? You just do one calculation. But if the reactant are given for both of them, then you have to set up two separate calculations. Okay, so that is the difference between 7.2 and 7.3 that you see here. Okay, so pretty much this chapter section is similar to 7.2, except we're gonna set up two separate equations for each reactant that is provided. Okay, and also the another thing that we learn about this is the percent yield calculation. Here are more problems on page 136. Okay, so I highly recommend you to actually do these two problems yourself, okay, without looking at the key first, okay, because this is going to be a great evaluation that you can do right before you actually go into the exam, because without being able to do any of these problems, you are not going to do well on the exam. Okay, so if you are be able to do this on your own without any help and without any what do you call, like looking at the answer ahead of time, you will do just fine for the exam. Okay, so that means in this case, make sure that you know how to do this. Okay, and then don't forget to check your answer against the key. Okay, so things that I would like you to correct would be this 2.55 m. Okay, so cross that out. Okay, so pretty much the question asking you to find out molecule of H2 that would be produced when 150 milliliter of HBr, okay, is completely react with the iron. So that means in this case, you will need to use the density to do some calculation as well. Okay, so jot down the density of HBr. Okay, so cross out that, because this unit here you will not learn until 122. Okay, so you don't know about this unit yet, so you're gonna learn about this unit in 122. So cross that out, and let's use this density information instead. Okay, so again, practice this and then check your answer against the key. So here is the summary of this chapter section. Okay, so pretty much we learn about limiting reactant, theoretical yield, and percent yield. Okay, so after watching this video, please start working on your online homework soon.